this function is based on generalization.
Yeah. Yeah. Yeah.
We knew that theta values on one lagging.
Yes. Yes. Okay. Yeah.
And we consider the abstraction of interval.
Interval. Yes.
N of subsets.
Yeah. 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 Okay. We end
This is
one. Yes. Okay. Okay, so these are this union. So they're really okay. So this is actual partitioning of the.
We are currently experiencing technical difficulties.
Yeah. Okay. Well, yeah.
Okay, there it was. You probably don't want to mirror it. If you don't have a remote, it's hard to work without it. Go to settings, display. Hold on, option and right. No, it took me a while to figure it out because I never mirror it. Just use a remote.
Okay, so can you use this?
No, I think it's me.
Are you on the chair?
I'm the chair.
Oh,
We could both try. It was supposed to be me, but I got here like 1 second too late. All right, now that we've figured out how to make computers work, I'm pleased to introduce the second talk of the afternoon session, or possibly the first talk of the second afternoon session. Our speaker will be Shamil Shakirov, telling us about an elliptic generalization of A1 spherical DAHA.
thank you. Thank you. Thank you. All right. I would like to thank the organizers for inviting me and for giving me a chance to speak here in Tokyo. It is very nice. A few words about what the subject is of the talk that I will present today. DAHA is an important algebra, which I'm sure many people here are familiar with. And I will be a little bit more technical in a few slides, but I want to say that there exist, and in fact many elliptic generalizations of DAHA. And this should not be a cause of confusion, and this is why we're using N here, because this is just a generalization, not some generalization which pretends to be all encapsulated. So this is a work in collaboration with my longtime colleague, Sven Ottemar, who is now in Toronto. All right, so what is DAHA? Well, I don't want to be technical because I will really only need spherical DAHA, and in fact I will only need spherical DAHA of type A1 for the purpose of this talk, and so it is enough to say that it's an important algebra that has been introduced by Ivan Cherednik in the 90s. It's an associative algebra. It can be defined by generators and relations. and very useful in many contexts. It can be presented using certain shift or difference operators called the Dunkel or the Mazur-Lustig operators. We will need none of this. We will not need any of this. So the algebra has a number of important applications, including, famously, the proof of McDonald-Constantin conjectures, done by Cherednik uniformly for all root types in 1993. And then later, for example, I just give two applications. One is construction of certain knot invariants that generalize the Jones polynomials of knots. They are called DAHA Jones by Cherednik himself, and that is 2013. This is also related, for those who may have heard about this, to the subject known as refined Simons theory and to knot homology, Kovanov-Rosansky knot invariants. A third application is action on the Hilbert scheme of points in algebraic geometry of the spherical subalgebra of DAHA. And that is the work of Gorsky and Nigud in 2015. Also very interesting. All right, so now that I've said this, I will present the main protagonist, which I will generalize. This is spherical DAHA of type A1. For type AN, spherical generally means that we are considering a subalgebra that preserves symmetric functions of n variables, x1 to xn. And in this project, we'll be only concerned with spherical DAHA of type A1. And it can be explicitly presented using two difference operators here. So this is a brief formulation of the problem where you don't have x1, x2, you only have one x and respectively the shift in x. And you're acting on functions of a single complex variable, preserving symmetric functions in the sense of inversion of that x. It can be checked that these operators preserve indeed symmetric functions. And they act on a certain space of functions of a single complex variable. We don't need to be very specific here. It can be any reasonable space. If one wants to be fully specific, one can take Laurent polynomials of bounding degree. But of course, you can be more general than that. Okay, so two explicit operators. What can be said about this? Well, they form certain algebra. What is interesting about this algebra? Many things. So for one thing, relations. I write one example of a relation in this algebra. This is sometimes called the Q-Sur relation, because it's a Q deformation of the very well-known Sur relation in representation. Of course, this is not to mean that there is only one relation here. There are many relations, it's just one of them. Okay, next we have automorphisms. This is an algebra presented by generators and relations, and so you can define polynomial automorphisms which may satisfy certain relations and form a group. And in fact they do. Here you can define this both A and B. Here by polynomial formulas, both A preserves the generator away. And similarly,
sorry very much for disturb. Is it Onsara algebra in the sense of Paul Taurenga?
in the sense of what?
Paul Taurenga.
Paul Tauren.
Maybe my pronunciation is not good. Wisconsin University.
Ja, really good.
I just don't hear what it is.
Paul Terwilliger?
Can you?
Sorry, Paul Terwilliger, I believe his name.
On-site algebra. Which of the are you referring to the algebra generated by OA or B or to something else?
But that Q-cell relation is, looks very similar to the cell relation of Onsara algebra.
Oh, I understand. SIR relations appear in many different contexts. So they also appear in quantum groups. And this is so general that it's likely not necessarily related to one specific instance.
But yeah, your Q-cell relation has a right-hand side extra term that's very looks very similar to that
Okay.
one of Osaka algebra.
Okay, well, thank you for pointing this out. I will definitely take a look at that. So, to continue, we have polynomial formulas for the action of automorphisms on this algebra. And you can check that this is indeed an automorphism in the sense that if you act on a relation, it becomes a relation. And then what you can check further is that these automorphisms A and B satisfy ABA squared is 1 and ABA equals BAB, which are the generating relations of PSL to Z. So spherical DAHA of type A1, despite being very simple example, already exhibits the action of PSL to Z by automorphisms, which is a very interesting feature of DAHAs in general. Okay, what else? Well, we have eigenfunctions. The operator OA has non-trivial eigenfunctions labeled by a natural number J, which are called Macdonald polynomials. And here is an explicit formula for OJ from 0 to 1, 2, 3, 4, and so forth. Depends on two parameters T and Q. And the eigenvalue is also explicit. It's this, given by this combination. So a remark is in order, which is one of the central points in my talk, is that Macdonald polynomials are associated from the point of view of integrable systems with trigonometric Janach-Schneider many-body integrable system. And in fact, the operators that I write in this slide are nothing but, so the operator OA is nothing but an example of this integrable system for the case of two particles. In the center of mass frame, where X is the unique non-trivial coordinate in the model. This will be important for them. Macdonald polynomials form a simple algebra with respect to multiplication. If you multiply two eigenfunctions, two Macdonald polynomials, you get a linear expansion in eigenfunctions with some coefficients, which are called Littlewood-Richardson or Verlinde coefficients, depending on the context. And last but not the least, you have a very interesting property which is called finite dimensional representations. For this specific value of t, which is negative q to the negative k over 2, with a choice of k, which is sometimes called level in some contexts, and it's a positive natural number. The ideal spanned by polynomials pj of x with j greater than k can be declared negligible. What I mean is that you can take a quotient with respect to this ideal, so all polynomials higher than certain one, and the quotient is a finite dimensional, k plus 1 dimensional, in fact, vector space.
But there are others, right? There are three different conditions. If one of the cases don't have finite dimensional representation,
there are others, yes. This is just one. But we will work with this one. Not only the multiplication becomes a finite dimensional operator, but also other operators become finite dimensional matrices as well. So, for example, most importantly, the automorphisms A and B. In general, I remind that these are these formulas here. In general, these are not inner. So these are some automorphisms of the polynomial algebra, but they are not given by conjugation by any element, in general. However, specifically for this case, t is equal to negative q to the negative k over 2, they do become inner. And they are given by conjugation with finite k plus 1 dimensional matrices, which I call dA and dB. This is this is to mean that DB, for example, realizes conjugation by DB realizes the action of the automorphisms both B. There are explicit formulas for these endomorphisms, DA, DB, or equivalently T and S. They are given by these explicit formulas here, notably the S matrix, which is another parameterization of the B automorphism, is constructed from the special values of the Macdonald's polynomials at special points. So defined matrices satisfy the same conditions as the automorphisms satisfied, and generate PSO2Z. So I told you all of this collection of probably well-known facts about the spherical DAHA of type A1, because this will be the starting point for our project with Shamil Shakirov of generalizing this to elliptic direction in a certain sense. I want to comment on this slide, what do I mean by elliptic generalization, because this may be a source of confusion, as many other elliptic generalizations of DAHA do in fact exist. So which generalizations of DAHA are known? Well, first of all, root system generalizations. You generalize from A1 to other root types. And this goes starting from the original work of Cherednik in 1992, where he defined DAHA for reduced root systems. Then, historically, I think the next is C-Check-CN by these authors. And this was generalized further by Ettinghofer-Glonkov, Reins in 2006 to what's called G-DAHA, generalized DAHA. This is a far-going generalization of the C-Check-CN case.
Oh, that paper is C-Check-C1. It's a later paper that does the C-Check-CN,
I see.
which I was not involved in.
I see. Okay, and in particular, in this family of generalizations, you can single out elliptic DAHAs. There are two papers I can mention. One is by Cherednik himself. It's the elliptic difference paper in 1994. And then the other one is the paper by Reins in 2017. And they use mainly DAHA for affine root types to construct what's called elliptic DAHA. Our generalization will be different. So, and how exactly will it be different? Well, let me say a few words about this. There are other ideas on how to generalize DAHA in other directions. For example, one is topological direction, where you take an algebra. Okay, of course. Okay, so you take one important property of the algebra and you take it as a guiding principle for generalization. So one property which is certainly something that comes to mind is the action of an interesting group by automorphisms. For DAHA, this is PSO2Z. And what can generalize PSO2Z? Well, it can be generalized to a mapping class group of a higher genus topological surface. And this is a project that we pursued with Semyon Artamonov in 2019, where we constructed a new algebra, generalizing DAHA, replacing PSO2Z by a genus 2 mapping class group in type A1. And this has been successful. Indeed, an algebra exists, and you can find generators relations. You can prove that the mapping class group of genus 2 acts. And it's no longer PSO2Z, or in fact not a special linear group of any rank, anything like that. Yeah.
But also the isomorphism group is bigger. PSO2Z cross Z2 cross Z2. And like the binary group is symmetry of the big diagram before. Do you expect those discrete symmetries?
Sorry, what you're saying is...
Isomorphism of DAHA is not PSO2Z, it's PSO2Z cross Z2 cross Z2.
Yes, but for spherical DAHA,
That's very correct.
no, we don't discuss that. We are working with the PSO to Z part and generalizing. So I assume that our algebra also has this extra symmetry. Okay, this is one direction, and then another direction which we pursued recently with Semyon is the direction of integrable systems. And this, I hope, gives you the idea of what I mean when I say elliptic generalization. The original spherical DAHA is associated in the way that I mentioned earlier with the trigonometric Ruzhina-Schneider integrable system through Macdonald functions. And it's an interesting question whether one can replace this integrable system by a more general integrable system, preserving some properties of DAHA. And this project was designed specifically to answer this question. We consider a more general integrable system, so this is some classification, some simple classification of integrable models based on periodicity properties in coordinate and momenta. So as usual, you have three cases: rational, trigonometric, and elliptic. And the model can be rational, trigonometric, or elliptic in either the momentum or the coordinate or both. So the original model that DAHA is associated with is the central square here. This is the trigonometric Ruzhina-Schneider. And then we ask a question with Semyon: what happens if we replace trigonometric Ruzhina-Schneider with a coordinate elliptic Ruzhina-Schneider? Will there be an algebra that plays the same role for elliptic Ruzhina-Schneider that DAHA, spherical DAHA, plays for trigonometric Ruzhina-Schneider? And we construct such an algebra here. In this sense, it's an elliptic generalization of DAHA. And of course, it's a very interesting question. What is, if any, the relation to the previously constructed elliptic DAHAs? Okay, so going straight to the integrable system. We consider here elliptic Ruzhina-Schneider of type AM. And most famously, it probably has a Hamiltonian, or a sequence of quantum commuting Hamiltonians. And you can define what's called a stationary problem, where you require the Hamiltonians to mutually commute and to be diagonalized on a certain system of eigenfunctions with common eigenfunctions and some eigenvalues. However, there is a more general problem that you can associate to this integrable system, and that is called non-stationary problem. The description of non-stationary problem is so far vague, but many properties of non-stationary problem are already known. So it's an equation which is non-stationary in the sense that it corresponds to time evolution in quantum mechanics, as opposed to stationary energy or eigenvalue problem. It should reduce to the stationary problem in the stationary limit, which is well known to be the limit s goes to 1 in these parameters here. And the wave function, so the solution of the non-stationary problem, is also known. Here it is. This is the function. It's called FGLN. Many people call it non-stationary Ruzhina-Schneider function. Here x is the coordinates of the wave function. Y play the role of indices or energy levels in the stationary language. P is the elliptic parameter. S is the non-stationary parameter. And Q and T are the Macdonald parameters, the same as for usual DAHA. So this formula comes from algebraic geometry, and it has a meaning of computing a certain character in K-theory of an appropriate algebraic space, which is called the affine Lamont space of type GLN hat. It's a sum over n partitions, integer partitions, written here, and the integer partitions in algebraic geometry have the meaning of labeling fixed points in K-theory. The weight, which is the summand here, represents the contribution of the character of the operator that you're computing. And it's written in terms of orbifold Nekrasov functions, just the same as in the previous talk. And there are some conventions here, the x is a periodic, etc., etc.
Oh, sorry. Wouldn't one expect data functions in the elliptic case?
Theta functions.
Yeah, instead of these products.
Well, it's an infinite sum, and sometimes it can be summed exactly, but not always. So it's an elliptic function which sometimes can be expressed in non-elliptic functions, but in general we only have the series representation.
Yeah, but I mean the n lambda mu k.
Oh,
products
this part.
of data functions.
Okay, so there are two types of ellipticity, as denoted in this slide. One type of ellipticity is moving from the central square to the right, and this is coordinate elliptic. This corresponds to promoting this Macdonald function into an infinite series governed by the parameter small p, which is not summable, but it is an elliptic function somehow, of some sort. And then the second type of ellipticity is what's called dual elliptic here on this slide. And this corresponds to promoting the Nekrasov factors to theta functions. It's an orthogonal problem to what we're considering. Okay, so the machinery of algebraic geometry or quantum supersymmetric quantum physics, if one likes, provides a beautiful explicit formula for the eigenfunction of the model. This formula should be thought of as a generalization of the Macdonald polynomial. Some people call it elliptic Macdonald function. Okay, we are only interested in A1, and this makes matters significantly simpler. You only consider functions psi j of a single argument x, and j is the replacement for the y variable before through this discrete transformation. Okay, so the function is called fgo2, and the arguments are chosen in such a way to reproduce the usual Macdonald polynomial. It's a series expansion. In the zeroth order, it's an elliptic, it's a usual Macdonald polynomial, and then it's a series expansion where you get more and more Macdonald polynomials somehow.
But Macdonald polynomial is one variable.
Yes. Symmetric under x goes to x inverse.
Is it a special function?
It's a special function. It's called Q alpha-spherical. Yes. So psi functions, these non-stationary wave functions of the elliptic model, just as Macdonald polynomials, form a simple algebra with respect to multiplication. Now coefficients depend on two extra parameters p and s, and they can be called generalized Littlewood-Richardson or generalized Berlin coefficients. Okay, here comes the first remarkable property of the model, which we do not prove, and we state as a conjecture. One can define finite dimensional representations at t equals negative q to the negative k over 2. What it means is exactly the same as in the Macdonald case. The ideal spanned by the higher psi functions can be declared negligible. All the operators that we consider reduce to matrices, k plus 1 times k plus 1 dimensional matrices, just like in the usual case. Okay, now here is probably the crucial slide. Finite dimensional representations of PSL to Z for the elliptic Lunar-Schneider. Again, this is a conjecture. We do not prove this. Can one generalize the formulas through special values of the Macdonald polynomials written, for example, in the work of Kirillov Jr. On special values of Macdonald polynomials to elliptic case? By some experimentation, we found that this is possible. Namely, one needs to construct the matrix S in the following way using these non-stationary eigenfunctions of the elliptic Schneider model. The formula is almost literally the same as the formula from Kirillov Jr.'s paper, except there are correction factors where you put either the elliptic parameter or the non-stationary parameter to vanishing. The T matrix is not changed at all. Now, defining these operators S and T, one can conjecture and check that these operators satisfy the following relations here on the board. These relations at first do not remind SL2Z because of the strange shifts in parameters P and S. But you can remedy this quite easily by introducing hat dA and hat dB to be these operators times shift operators of this kind. In terms of hat operators, you now literally get the definition of PSL2Z. Okay, a conjecture is good, but what can we get out of it? How do we prove that there is an action of SL2Z in the elliptic integrable model?
Sorry, can I just, your notation here, because this doesn't look literally like PSL2Z to me. You don't write equalities, so.
Oh, probably, are you referring to this 4 here?
Or no, I'm referring to your.
Oh, these?
Yes.
Okay, this is projective representation.
Okay.
This is the usual story in the Macdonald polynomials. The representation is never literal. It's always
Yeah, okay.
And presumably it's SL2, not PSL2.
No, it's still PSL2, but it's a projective representation.
PSL2 should be a square.
And this issue is also so this is SL2Z projective representation.
So, Shamil, I think if you include those discrete symmetries I was talking about, it will be clearer than that. I think that people wonder is one of those issues.
I see. That's very useful. Thanks.
So we have this in our paper with Gukov and Novak to discuss this project together.
Okay. Okay, so how do we prove the action of SL2Z?
Also, there are some factors that you don't construct the abstract algebra, you construct its representation on those which are generalizing this Macdonald polynomials, right? Because the relations, right, they're tied to the choice of this finite dimensional representation, right?
Yes.
So if you take a different finite dimensional representation in spherical DAHA, you get different relations?
No, it's you get the same relations. It's just you get a different series of representations of the matrices, of the operators. There exist abstract automorphisms of certain abstract algebra, which satisfy relations ABA is equal to BAB, regardless of choice of parameters small q, small t. But then for different choices of these parameters, these abstract automorphisms can be represented by concrete matrices.
But you're making a choice. You're saying Q plus Q plus 1.
Well, I'm telling historically how we arrived to the algebra. We arrived through this choice of T and Q. We found the relations and then we wanted to prove it. But if you look at the paper, it's not structured like this. We state the algebra and we prove that there is an action. So key is construction of the algebra of operators, and just as with the spherical DAHA, we define 2 operators, OA and OB. OB, just as in the spherical DAHA, is just multiplication by x plus x inverse. OA, just like in the spherical DAHA, is the diagonal operator on psi functions. Now, diagonal operator on psi functions, we choose the same eigenvalues, by the way, does not have an explicit formula in terms of difference operators, unfortunately. But you are free to define such an operator at least. We studied the adjoint action of automorphisms on the generators and asked the question, are they preserved? In the sense that can you, of course they are not literally preserved, but is the algebra generated by them preserved? And the answer is negative, it's not preserved. The adjoint action of the automorphisms produces new generators from OA, OB. And we decided to label these generators by this is somewhat hard to motivate. This is just how it comes out from mathematics. By elements of the free group of two generators. There are two generators, small a, small b, which you can think of as being related to the action of automorphisms. Roughly speaking, automorphism A shifts you in the A direction, and automorphism B shifts you in the B direction. And exact formulas, now from this case we zoom into the case that we were able to prove in the paper. And this is the case k is equal to 2. We only consider k is equal to 2, although all conjectures we believe are valid for the general k. For k is equal to 2, the formulas for the action of automorphisms on the generators are like this. And you can see that the upper indices are related to the elements of the free group as we defined. The S automorphism exchanges A and B, and then it acts on G by exchanging these labels as well. Okay, but what other, so now we define an algebra which is generated by generators OA of G, OB of G, for G in the free group, over a field, which is the field of rational functions of the parameter BQ, which is the remainder of McDonald parameters here. And the natural question about this algebra is, what are the relations in it? We study the relations using the finite dimensional representations, and then we postulate them. Here is the list of relations. There are 11 families parameterized by elements of the free group, and most of them are really simpler than they look. So for example, if you look here, for example, relation 7 is nothing but the Q-SIR relation, or generalization of the Q-SIR relation. There are many relations which are much simpler than what you can find in the spherical DAHA. For example, relation 2 states that the product of OB, OA, OB vanishes. How can this be possible? Well, this is all because of specialization k is equal to 2. So we are only considering a very simple case of k is equal to 2. In general, for general k, we do believe that the algebra exists, but the list of relations will be significantly bigger. In any case, you are free to define such an algebra.
Sorry, this is relations for arbitrary genus or genus 2?
Genus is 1 in all of this story.
Is it connected with the scaling relations for Riemann surface?
You can think about this as scaling relations for the torus. But the torus has two cycles A and B, and now in addition it has also this small letter g, which is somehow elliptic degree of freedom. It's a very interesting question if one can sort of consider a marriage of this project with our previous project with Simon and consider a genus 2 elliptic algebra. Who knows? Okay, this algebra generated by the relations and generators, generated by the generators with the relations above, is the elliptic generalization of spherical DAHA of type A1 that we suggest in this project. We prove that the ideal of the relations is invariant under the action of automorphisms. And then automorphisms satisfy the defining relations of SL to Z on the algebra, which is the quotient of the algebra by the ideal of relations. And operators and automorphisms have 3 by 3 matrix representations with elliptic functions. Why 3 by 3? Well, because if you recall, k plus 1 dimensional matrices, and k is 2 here. So 3 by 3. And here are the representations. The representations are strikingly much more simple than the list of relations for the algebra. And you can think about the list of relations as being sort of the construction works to justify that these two matrices satisfy the relations that they satisfy. On the other hand, the algebra of operators is very interesting in and out of itself, and it is expected to be related to many other branches of representation theory, so whenever there is an interesting algebra, it is good. So I want to comment that here I'm using a notation pexp, which is the platistic exponent. Very familiar to combinatorialists, but I don't know if to all. And this is a notation which can be recast in terms of the elliptic gamma function. So essentially, all of these matrix elements can be written in terms of the elliptic gamma function, with a few Pochhammer corrections. So these two matrices satisfy identically for all P and S in the domain of definition of these functions, the relations of SL to Z. And for P is equal to 0, this representation of SL to Z reduces to non-elliptic standard representation given by the McDonald parameters. So this is a new elliptic representation of SL to Z. In the remaining few minutes, I want to conclude that we constructed an algebra that plays the same role for the elliptic Ruzhina-Schneider integrable model that spherical A1 DAHA plays for trigonometric Ruzhina-Schneider model. We only consider the case k is equal to 2, which corresponds to three-dimensional finite dimensional representations. We suggested to call this algebra an elliptic generalization of spherical DAHA type A1 at k is equal to 2. And we very much hope to continue our work to define and prove the corresponding results for k is equal to 3, 4, 5, and so forth. We proved that SL2Z acts by automorphisms of this algebra and constructed a three-dimensional matrix representation for both the algebra generators and automorphisms with elliptic functions. We conjecture that the action of SL2Z holds true for any k. Okay, there is some comments on the origin of the elliptic functions psi j, which I think I can safely skip. This is very well known. In algebraic geometry, it's a character. In physics, it's a partition function in the presence of a surface defect. And in integrable systems, it's a non-stationary wave function. It's interesting that similar but not identical functions appear in the work of Felder-Varchenkov as solutions of QKZ equations or QKZB equations on the tori. We tried to make a literal match between our functions and their functions, and it appears that they are different, at least at the first level of consideration. Last but not the least, there's a conjectural relation to knot theory here. Namely, you can define an invariant of a torus knot following the work of Aganagic and myself with what is sometimes known as refined silence theory. A formula for such an invariant where you replace usual SNT matrices by elliptic SNT matrices produces to you, for every torus knot, an invariant taking values in elliptic functions. And it's interesting to interpret these elliptic values, not invariants, in terms of some not homology theory, if any. Thank you for your attention.
All right, are there any questions?
So, do I understand correctly that you have these relations, right, for different choices of k? So basically, there's like there's an abstract algebra relations which you don't know yet, and then if you specify them, when you look at the representations of certain choice of k or other series from DAHA, right, you get different relations. But like, so you hope that there's universal there are universal relations which you don't know yet, and you hope that you can recover all of the k. You can guess what they are, but look in a different dimension.
That is correct. Relations generally split into two parts. There is a general part or universal, which is, we hope, true for any k, or true abstractly, regardless of specialization to k. And then there are ones which are specific for a particular k, and are completely disappear or get modified when you increase k. And of course, the relations that I wrote for, many of them are only true for k.
Yeah, the second question about this eigenvalue equation. So why did you pick this eigenvalue equation for OA? What was the justification? So like, there's no deformation on the eigenvalue.
Well, because, okay, a physics argument is that this eigenvalue is expected to be deformed in the dual elliptic.
Yes, it looks like the dual model, right?
Yes, but for this model, it's not expected to be deformed.
The elliptic RS is deformed. The dual one is not deformed. Which one is this?
This one is the, not the dual, the direct.
Okay,
Okay.
I just wonder about you some, in joint paper, you gave some interpretation of double Magomed polynomials, one variables, genus 2, as eigenfunction of family of free mutually commuting operators. Can you do it for genus 3, when you have 5 variables and 5 differential equations mutually commuting, which functions are eigenfunction of this family of 5 operators?
Thank you for your question. Very good question. We spent quite a bit of time on this with Simon. The answer is you can do this if you forsake the parameter t. But if you want 2 parameters q and t, it is not possible.
Any other question?
Okay, and can you treat as a scaling algebra? Because I don't know, maybe it is well-known conjecture that DAHA genus G should be scale algebra of Riemann surfaces of genus G, and G punches in general position.
Yes. You will get a representation of this genus 3 scaling algebra by difference operators.
Okay.
But no t, unfortunately.
Any other questions? All right, well then let's thank the speaker again. And I believe we resume in 15 minutes. It's about 4:17.
Да, вот это будет.
Я.